Okay, good afternoon. I hope I'm audible. So, welcome back to the final sessions on NME92, Mechanics and Control of Robotic Manipulators. So, on previous Saturday, on I believe it was a couple of days ago, we have covered the final session, final session based topics on the course. So, last week we were mostly discussing about you know the design of a cascaded control. So now that we have covered all the courses or all the topics for the entirety of the 9 weeks course, we are left with this one last session where I intend to cover, or I intend to speed run through all the topics that we have covered from week 1 all the way to week 9. And I won't be talking everything in detail because, as you can see, there are almost 96 slides. But I wanted to make this session as just like a refresher. If you want to know something more in detail, in case if you want to know some specific derivations or some topic to discuss in detail, I would recommend you to visit the previous recordings of that corresponding week. And this session is only intended for a speed run through all the topics. And then if you have any doubts, probably we may be able to clarify this on live. So yeah, moving on. We'll start with week 1 topics, which were more or less covering the basics of robotics. Specific to our course, in our course we mostly talk about robotic manipulators. And in robotic manipulators, what do we have? We have even further classification. One is called parallel robotic manipulators, and the other, which is what we are studying in this course, we call them serial robotic manipulators. And then in case of a robotic manipulator, how do you define a specific configuration of a manipulator? What are the variables involved? All these things are basically covered in week 1. So we actually began, or we started our course on general definitions on robots, the one which is given by a Robot Association of America, which is a well-structured definition. It's nothing but an industrial robot is a reprogrammable or multifunctional manipulator designed to move materials, parts, and tools or specialized devices through variable programmed motions for the performance of a variety of tasks. So it's a very well clearly cut definition, from an industrial point of view. It more or less gives a lot of clarity on what an industry really requires from a robot. And recently, we don't really need a robot to assume a physical configuration or a physical state. It can also be virtual. So as per the recent definition, a robot is nothing but an intelligent agent, be it physical or virtual, capable of doing tasks autonomously or with guidance. So one example is chatbots, actually. So it does not have a physical entity. It lives on a virtual space. So our typical definition of robots, having physical link or physical mass, it need not be necessary for a more modern definition of robot. And from the context of this course, robot is nothing but an electromechanical device or a mechatronic system with sensors, electronics, and are also guided by computers and controllers. So an electromechanical system, which has a mechanical architecture, like for example, a manipulator arm, and it is basically controlled by an electrical system running throughout, its course. For example, if you use motors to actuate, that becomes a mechatronic system. And it is also, we also require sensors so that if you want to make sure that your robot wants to go from if your robot want to go to a specific location, you need to be sure that the robot has reached that particular location, and for that we use sensors. And also, what do we do with this sensor data? All these things are basically decided by a motion controller that we can develop based on our application. And also, we have seen when and where to use robots. So typically, mostly from an industrial point of view, we employ robots on tasks which can be classified as dull, dirty, dangerous, or difficult, for a human being to perform. Dull in the sense like it's not very inspiring for a human being to do, probably repetitive jobs, and dirty jobs, probably, things like manhole cleaning. These things are actually more these days, more and more such jobs are being replaced by robots instead of deploying a human being for those tasks. And there are also tasks which are also dangerous, probably extraction of hazardous nuclear wastes from sites which are which are nuclearly hazardous. So instead of deploying a human being, we can send a remotely controlled robot to do some intervention. And another is, if the task is so difficult for a human being, we can again use a robot for tasks which are difficult. And then throughout the course, we use a term called effector or end effector. So just to clarify what an effector is, an effector is any robot or a robotic device that has an effect on the environment. So this effect can be, different phenomenon. So in case of a robotic manipulator, as you can see on the left-hand side, this one, it's a typical robotic manipulator. In case of a manipulator, the effect on the environment would be, the motion of the objects within its workspace. So if there is an obstacle or an object within the robot's workspace, the effect on the environment would be, the manipulation of this object, maybe to pick this object and place it somewhere else within the workspace, or pick it and reorient it in some other workspace. That is the case for manipulator. And the second one over here is actually a mobile robot. And specifically in this case, it's a wheeled mobile robot. Out of all the possible mobile robots, this one is a wheeled mobile robot. And in case of a wheeled mobile robot or any mobile robot, the effect on the environment is the motion of the effector itself. So in this case, this is the effector and its effect on the environment, due to the traction force imparted by the wheels, the effect on the environment would be the motion of the effector itself. That is in the case of a mobile robot. And to the far right extreme of this slide, or what you basically see is a combined wheeled manipulator actually, or a mobile manipulator, which has a mobile base, a wheeled mobile base, and on top of it you have a robotic manipulator attached on it. So it has both of these attributes of a robot manipulator as well as a mobile robot. And another term that we would be coming across more often during this course is controllers, which is to get the effectors to produce the desired effect on the environment based on the robot's task. So a controller would give the appropriate control signals to the actuators. So in this case, the actuators would be the motors that have been placed at the joints, depending on the error between the desired position and the actual position. And in case of a mobile robot, the controllers would impart the necessary torque to guide the mobile robot along the desired direction. Maybe it can go forward, or it can go backward, or it can go sideways, or in diagonal ways, whichever be the case. So that is what the controllers do. And again, we have also seen the type of manipulators. So the one to the far left extreme of this slide, we can call this as a serial manipulator. So the reason being this being called as a serial manipulator is, the manipulator essentially consists of a series of links, which are connected, one after the other, like as a series of bodies using actuators. So typically, the most common actuators used in these sort of robots are, rotary or uh, just probably brushless DC motors, which basically actuates these revolute joints, right? And they are attached one after the other. It does not even have any closed chains like a 4-bar mechanism, something like that. There are no closed loops. And at the middle of this slide, what you see is actually a parallel robotic manipulator. Do you? I've got a question. Do you have a course on parallel robots offered by NPTEL? No, I don't know if there is a course specific on parallel robots, but there is a more comprehensive course on robotics, which actually covers the mechanics of serial as well as parallel robots. And it is offered by Professor Ashitava Ghoshal from IIC Bangalore. So that is also, it covers a lot of topics in great depth. And it's also a 12-week course, if I'm not mistaken. So there, in those course, we'll also cover, the mechanics of parallel robots as well, right? So yeah. So in this case, at the middle of this slide, what you see is here is a parallel robot. So the defining feature of a parallel robot is that, a base frame or, the ground is connected to a motion platform or a moving platform using, a series or several legs. In one way, you can consider these individual series of legs as serial robots, and a parallel arrangement of such serial mechanisms basically constitute a entire parallel mechanism. So the advantage of these sort of mechanism is that the loads are actually more evenly distributed. So parallel robots have inherently high payload, inherently high payload manipulative capabilities. And you would see, these things being used to simulate flight cockpits, or these sort of things are also used by professional race car drivers for simulation purposes. So these sort of capsules, they are capable of carrying the weight of an entire human being, and they are also simulate the forces that is imparted by a race car or even a fighter jet in real life. So as you can see, they can go up to multiple times the weight of that person themselves. So you can imagine the forces that is being transmitted by these sort of things. And another advantage of these mechanisms is that the actuators are more or less located near to the base. So in most of these examples, the actuator, the most heaviest component of a robotic system are the actuators. So if you consider this link, the actuators would be mounted on these links, and the total weight of this link would be on the lion's portion of the weights for all of these links would be contributed by the actuators. And in a serial robot, the actuators are everywhere. It's kind of floating. So the moving inertia as well as the rotational inertia of a serial robot is very high. And due to the fact that the robot has to carry its own weight, it may also lead to some accuracy issues. But in case of a parallel robot, since the moving masses are, most of the time it's fixed to the base, or if they are moving, they are actually very close to the base. Their moving inertia is actually very low, and as a result, their accuracy would be very high in case of a parallel robot. And over to your far extreme right of the slide is something called a hybrid robotic manipulator, which is a hybrid combination of a serial robot and a parallel robot. Could be mostly used in surgical applications, where sometimes you probably require a very high reach or a very high workspace of a serial robot. And at the end, you may probably require, very high precision of a parallel robot. Yeah, so those are the types of manipulators that typically one would encounter. And for this course, we are strictly limiting ourselves for serial robots. The mechanics of serial robots, which has the kinematics. We'll also see the statics. We also see the dynamics of serial robotic manipulators. Yeah. Then we also see some key definitions. So what we mean by manipulator, it's nothing but a set of bodies, connected as a chain with the help of joints. That is what we have seen so far. And what do you mean by configuration? It's a complete specification of location of every point of a manipulator. So for example, if you have a 2R robot like this, having two links, so this is, you can call this as a first link, this could be the second link. And at the end, you have a gripper, and the first link is connected to the ground using a revolute joint. Second link is connected to the first link using a revolute joint. And basically, a configuration means the complete specification of each and every point that is part of the manipulator. And to define the configuration of a robotic manipulator, you probably require a minimum set of independent variables. Maybe if you specify the variables as joint variables, you can have one variable over here, theta1, and another variable here. You can label this as theta2. So with these two variables, you can define location of any point at any time in space. So for a 2 degrees of freedom robot, you need two variables to completely define its configuration. Then another term that we would require in the context of a serial robotics, a serial robot is called the workspace. It is nothing but the total volume swept out by the end effector as the manipulator executes all possible motions. For example, if you consider your arm, the entire points that you can reach by your arm can be considered as the workspace of your arm. And then there are two possible variants of the workspace. The one is called reachable workspace, and the other one is called dexterous workspace. So in reachable workspace, each and every point within the workspace can be reached with any orientation, with at least one orientation, right? So any point in workspace can be reached with at least one orientation, right? For example, like if you consider your arm, if it is not fully stretched, you can reach any point with any arbitrary orientation, right? You can reach it with any orientation possible. But if you fully stretch your arm, the point that you reach by fully stretching your arm, it can only be reached by a single orientation. You cannot reach that same point by any other orientation. So if any point in workspace can be reached with at least one orientation, that is called a reachable workspace. And dexterous workspace is, it's the opposite of it, So points that can be reached by all possible orientations. So any point in workspace that can be reached by all possible orientation. That is about dexterous workspace. Then we have also we move on to this geometric modeling of a robot. So typically, in case of a robotic manipulator, to solve the kinematics, we have two sort of problems. The one is called forward and inverse kinematics. So since we have been discussing about forward and inverse kinematics throughout the entirety of the course, uh, we probably won't be discussing that too much in detail. So I'll just glance through this. So basically, kinematics is nothing but the study of motion without considering the forces or the efforts that basically causes the motion. Right? Something that causes the motion, we mostly neglect the cause of motion. And kinematics, from the context of a robot, from a robot, describes the relation between motion of the joints of the manipulator and the resulting motion of the rigid bodies which form the robot. So as you know, a robot like this 2R serial robot, which comprises of two links connected by two joints. And if this is the gripper, the position of the gripper is denoted by X and Y. So, kinematics is basically the mapping or the study of mapping this joint rotations. If I call this joint rotation as θ1, this to be θ2. So the back and forth mapping, from θ1 and θ2 to find the motion of this rigid body, X and Y, or, the other way around, if you know this X and Y, finding out θ1 and θ2. So those sort of problems is what is dealt in kinematics. And to be specific, there are two sort of problems, solving kinematics in one direction is called forward kinematics, and the opposite direction, we call them as inverse kinematics, where forward kinematics basically determines the configuration of the end effector for a given relative configuration of each pair of adjacent links. So for example, if θ1 and θ2 are given, finding out X and Y is the process of forward kinematics. And in case of inverse kinematics, it is nothing but for a given desired configuration of the end effector, finding the joint variables which achieve that configuration. Right? So in case of inverse kinematics, the desired position of this end effector would be given as X and Y desired. And finding out these joint variables, θ1 and θ2, is actually the process of inverse kinematics. Okay, so moving on now, we are also in the process of describing the position and orientation involving translated and rotated frames. So as you know, a robot would be typically consist of a series of rigid bodies. And most often you would find it very convenient to, if there is a point that you want to describe, you would mostly find it very convenient to describe this point with respect to this joint rather than any other joint. So once you do that, eventually you will have to, map it to a final global frame, a fixed frame. So you would probably require mapping to and fro between different frames, because a rigid body can be easily represented by a frame of reference. A rigid body like this can be represented by a frame of reference that is attached, rigidly attached to this rigid body. For example, X, Y, or Z, whatever be the case. Because the position of this rigid body can be described by the position of the frame of reference, and the orientation of the rigid body can also be defined by the orientation of the three axes of the rigid body. And now that it is understood that representing a rigid body is much more convenient with frame of reference, you would also need some sort of a mapping, to make the mapping between various frame of references more convenient. Because you will have a frame of reference here, you will have something over here, you will have something over here. You will also have something at the ground, fixed to the ground. So that is why we require a mapping between frames of references. So as you can see, if you consider this to be a global frame of reference, it is oriented like this. ZA is vertically upward, YA is horizontal, and XA is coming out of the plane. And in this case, it is completely different. YB is going vertically up, ZB is also horizontal, but going from right to left, and xb is actually coming out of plane. So if a vector or if a point is defined with respect to frame B, how do we map the same vector to a different frame A? Knowing that we basically know the orientation between frame B and frame A, and also the position between frame B and frame A, how do we map this vector to this vector? So that is what I have basically written over here. So if this is nothing but a vector addition actually, so if I write out this vector addition, you will get it as the position vector of Q with respect to A is the position vector of B with respect to A, where B is the origin of this frame of reference, right? So this vector is nothing but this vector plus this vector. So I'll write it as position vector of Q with respect to B. That will be this vector. But if you take a look, we want everything to be represented with respect to the frame A. But here you can see this vector is actually represented with respect to frame B. So to make this homogeneous, if you want to add vector quantities, everything will have to be represented in a single frame of reference. So to bring this vector, vector P with respect to Q, we would have to pre-multiply it with rotation matrix A or B, which depicts the orientation between frame B and frame A. So now everything is expressed with respect to frame A. So that is how one would do that. And just by looking at the orientation of these two frames, one can easily detect what or how this orientation matrix can be assembled. So for example, in this particular example, the rotation matrix would look something like this. The full expansion of this rotation matrix ARB would look something like this. So I'll write out the first column, that is nothing but the dot product between XP and XA, YB, sorry, XB and YA, XB and EZA, and the second column would be YB and XA, YB and YA, YB and EZA, and the third column would be ZB dot XA, EZB dot YA, EZB dot EZA. So these are nothing but the angle that XB makes with respect to XA, YA, and ZA. And the second column is nothing but the angle YB makes with respect to XA, YA, ZA. And the third column is nothing but the angle ZB makes with respect to XA, YA, and ZA. And from this figure, as an example, XB dot XA would be, I suppose, XB and XA are along the same direction, so it's 1. And since XB is orthogonal to YA and ZA, their dot products would be 0, so it will be something like this. And so now we move on to the second column. YB is oriented along ZA, so that will become 0, 0, 1, right? And ZB is oriented along negative YA, so that will become 0, minus 1, 0. So this is how this ARB would look like in this particular example. So I may have to warn that our sessions may get terminated intermittently. So please feel free to join back, because I think by the last week our licenses have expired. So we'll probably have, probably half an hour for each of these sessions. Right. So yeah, that's about it for kinematics. Then we have also seen that a transformation matrix, which will, take care of the rotations and translations into a single homogeneous transformation matrix. So a transformation matrix, ATB, is nothing but a 4x4 matrix, where the first 3x3 elements would be the rotation matrix, right? And the final column, the first three elements of the final column is the position vector between frames A and B, and the fourth row would be 0, 0, 0, 1. So in this example, if the position vector between frame B and frame A is APB, the APB here corresponds to this thing, and the rotation matrix that we have derived here corresponds to this thing, and the final row would be 0, 0, 0, 1. And this is basically the position and orientation of frame B with respect to frame A. And if you want to go the other way around, if you want to express the position and orientation of frame A with respect to frame B, you only need to invert this matrix. Right? So taking this inverse of this matrix, you will be obtaining this. Right? Basically, inverse of this matrix would be, the inverse of that rotation matrix, or, since the rotation matrix is orthogonal, its inverse is nothing but its transpose. And inverse of this element would be, minus of ARB transpose APB, and the final row would still be 0, 0, 0. You can also obtain this relation by considering the fact that ATB multiplied by ATB inverse is nothing but an identity matrix. So if you transform from A to B and again transform from B to A, that is nothing but ATB inverse, you will get zero transformation. That is given by the identity matrix. So ATB, you know this by this term, and identity matrix is also it'll be of the form I 0, 0, 0. Then the final row would be 0, 0, 0, 1. And to obtain this thing, if you multiply this thing out and if you equate these things, you will be able to get each and every terms of this values. You will be able to obtain exactly these equations. So that is about the transformation matrix and its inverse. Then what do we have? Yeah, then we have a case of something what we call as compound rotations. So for example, if you successively rotate about various axes, so for example, if you have an axis like this, A, with z-axis like this, x-axis like this, y-axis like this. So what will happen if you rotate in a clockwise direction, sorry, in a counterclockwise direction with respect to z-axis? So if you do that, you will get z-axis would still be the same. X-axis would now be this. Sorry, x-axis would now be vertically upward, and y-axis would be now, would be like this, right? And now if you rotate with respect to this y-axis in this sense, right? If you rotate it like this, how would it look like? So y-axis would remain the same. X-axis rotated 90 degrees would be like this, and z-axis would now be vertically up. So this is y-axis. So I hope you can see what I have done. First, I have rotated it by 90 degrees like this with respect to the z-axis, right? So now we get a new axis like this. And on this new axis, I have rotated with respect to y like this. So we'll end up like this. So to get this final mapping, what do? We do successive multiplication of each of these individual rotations. So I'll do this. I rotated with respect to z by 90 degrees. Then I multiply I rotate again with respect to y by 90 degrees. So if I do that, I'll get this final transformation matrix. And the thing is that what I have done is I have made all the rotations with respect to the current axis, right? So if I rotate if I rotate with respect to z axis, now this becomes our current axis, and I rotate that with respect to y axis. Now this becomes our current axis. So if we are rotating or if we are doing any sort of transformation with respect to our current axis, we do this post multiplication, right? Post multiplication, when we transform with respect to current axis, or we call this as mobile axis. So what will happen if I do the same transformation, but instead of this current axis, I'll do with the fixed axis itself. So if this is the original axis, I'll do these manipulations with respect to the fixed axis alone. So the first rotation about z axis would be still the same. That will look like, z will be like this, x would be like this, and y would be like this. Exactly similar to this. And the second rotation, I will rotate with respect to the y axis of the fixed frame. Instead of this current frame, I'll rotate with respect to the fixed frame. So if I rotate 90 degrees, like so, with respect to this frame of reference, how would it look like? So this frame would now look like y-axis would be like this, out of plane, z-axis would be like this, and x-axis would be vertically up. So as you can see, I did the same operation, rotate with respect to z-axis, rotate with respect to y-axis, but every operation has been done with respect to the fixed axis. Now, as you can see, the final outcome here and here are both different. See, x-axis was earlier up, but earlier it was z-axis that was up. Now z-axis is out of plane, but x-axis is earlier was out of plane, but going in the other direction. So if we are transforming or rotating with respect to the fixed frame, we pre-multiply. So we do this z rotation first, then we pre-multiply with the subsequent transformation. That was rotation of y by about 90 degrees. So this was pre-multiplication. So if you apply this transformation on this matrix or this frame of reference, you will get this frame of reference. And if you apply, yes, so if I apply this transformation, the post multiplication to this frame of reference, you will get the final output as this frame of reference. Yeah, and if you apply this transformation, the pre-multiplication to the original frame of reference, you will get the output as this one, right? So yeah, that is about compound rotations. And we have seen some sample problems. I won't be solving this, but just to see, we have been given, 3 frames of reference, A, B, and C, and the transformation from A to B has been given as so and so, and A to C is also given as so and so. You are asked to find out the transformation matrix between C with respect to B. This is what you are asked to find out. And if you know this transformation, A transformation multiplied by B multiplied by B transformation with respect to C would give you the transformation of C with respect to A. And since in this question, both of these, either of these are actually given. This one is given, ATB is given, ATC is given. And to find out BTC, what will you do? So you will have to take the inverse of this and pre-multiply it with ATC. So BTC would be ATB inverse BTC. In this question, it is post multiplication. In this question, it is post multiplication, right? If you have a transformation from A to B, and if you also have a transformation from B to C, so A to C would be successive multiplication of A to B and B to C. Fixed of mobile frame, is it not required? No, it's not required, because mostly we use this for DS transformation. And in DS transformation, we always mention it with respect to everything is, eventually transformed into the current frame. But it is when it comes to rotation, purely rotation, when you are only dealing with rotation matrices, then it has to be specified with, with respect to which axis you will be rotating. But transformation in general, it will be mostly, defined with respect to the current frame. That's about it. So that is how you would solve this problem. Yeah, and we have discussed this question for the live tutorial session on week 1. Now we move on to week 2. Probably I'll have to move a bit fast regarding the summary. So in week 2, we have discussed the DH parameters, because DH parameters is actually a clever way of defining the relationship between frames of references between two rigid bodies. Because if you consider two rigid bodies, isolated in space like this, and if you represent these rigid bodies with respect to frame of references, maybe this is frame 1 and this is frame 2, you would require 6 parameters to define frame 2 with respect to frame 1, right? 3 positions and 3 orientations. So instead of that, if you are using this DH parameter method, you would only need 4 parameters, right? So it's a clever way of defining the relationship between two frames using only the transformations between x and z axis. So 2 rotations about x axis, one rotation and 1 translation about x axis, 1 translation and 1 rotation about z axis. So in total, we only require 4 transformations. And transformation about y axes are not being taken into consideration. So just by using only 4 models, you will be able to identify configuration between 2 frames of references instead of the usual 6. So that is where this DS parameters comes. So as I mentioned earlier, there are 4 parameters. We call the two parameters as link parameters, which represent the information between 2 consecutive joints. The angle between 2 joints and the distance between the 2 joints, we represent using link parameters. And there are 2 join parameters, which represent the information between, 2 links, regarding their relative orientation and, the regarding their relative distance to each other. So yeah, there are, as we have seen earlier, there are 2 link parameters, what we call as link twist angle and link length angle. So link twist is nothing but the angle between zi minus 1 and zi measured with respect to xi minus 1. And link length ai minus 1 is nothing but the distance, perpendicular distance between Zi minus 1 and Zi along Xi minus 1. So the two transformations are about are along or are with respect to Xi minus 1 frame of reference. Right? The first one is a rotation and the second one is a translation. And the other two, the remaining two parameters, we call them as joint parameters. They are with respect to Zi axis. So the first one is basically the orientation between Xi minus 1 and Xi along Zi axis. And the second one is nothing but the perpendicular distance between Xi minus 1 and Xi along Zi. So two transformation along Xi minus 1 and two transformations along Xi, you will get four transformations, which comprises the four DH parameters. So in this case, we have a frame of reference I minus 1 attached to link I, and we have a frame I, attached to link I. So how do you communicate the whereabouts of this frame with respect to this frame? So you do that by this DS transformation. So what you do is first you try to align this Zi minus 1 and Zi along Xi minus 1. So if this is Xi minus 1, so if you rotate an angle alpha I minus 1 with respect to Xi minus 1, now Zi minus 1 would become something like this. This is Zi minus 1. Right. So now the relative orientation has been taken care of. Zi minus 1 and Zi are being taken care of. Now there is a finite distance between Zi minus 1 and Zi, this much distance. So that you would take care of by this transformation, a translation along this axis. Right. So if you translate along this axis, you will end up with the second transformation. So now Zi minus 1 would be like this. Xi minus 1 would be like this. Right. Now that the relative position and orientation with respect to Zi and Zi minus 1 have been taken care of, now you worry about the relative position and orientation with respect to Xi and Xi minus 1. So the relative orientation between Xi and Xi minus 1 is taken care of by this transformation, right? If you rotate with respect to Xi axis by an amount theta I, Xi and Xi minus 1 becomes parallel. So I'll redraw it like this. Sorry. So after that, Xi minus 1 would look something like this instead of this earlier case. Now the only remaining thing would be is this perpendicular distance that you can take care of by this transformation, translate along Zi by an amount di. So this offset can also be taken care of. So that is how you transfer information between successive frames. So in this instance, Zi minus 1 and Zi, just by using transformations along Xi and Zi. Sorry, Xi minus 1 and Zi minus 1. And if you multiply these transformations, rotation, translation, rotation, translation, you will end up with the transformation matrix from I minus 1 frame to ith frame. And it would look something like this, a 4x4 matrix. And with that, you can actually define the kinematics. If you know this general frame of reference, I minus 1 to I, by substituting the appropriate DH parameters to each of these parameters, you will be able to get all the transformation matrices, like from 0 to 1, 1 to 2, all the way to n minus 1 t n. And if you multiply this throughout successively, you will get this transformation from 0 to n, which is nothing but the forward kinematics equation. And then as an example, we have in the live lecture, see how to assign the frames of a spherical manipulator or an R parallel R, R perpendicular R parallel P, where the first revolute joint and the second revolute joint are perpendicular, and the second revolute joint uh, is also perpendicular to this prismatic sliding joint. So this should also be perpendicular, probably a mistake. So in effect, you will get a spherical parallel roof. So in assigning this DS method, first you do is you first assign the Z-axis frame of references. So the ground frame will have, the first joint will have Z1 pointing vertically upward. The second frame will have the frame of reference pointing along this direction or this direction. Maybe as per the question, we can actually have it like this, no problems at all. And Z2, since being a prismatic joint, Z2 would be along the axis of translation. And you also need one more frame of reference for the ground, that is Z0. You can consider this to be coincident. So once you have identified the Z-axis, now you need to fix the X-axis. So typically, X-axis would be common perpendicular to the current axis and the subsequent Z-axis. So in this case, Z2 and Z1 are perpendicular. So the common perpendicular would be along this axis. So X1 would be like this. I'll select X1 like this. And for convenience, I'll choose X2 like this. And Z1, sorry, this is supposed to be Z2. And since Z2 and Z1 are like this, common perpendicular would be along this direction. So I can choose X1 like this, right? And if you use this DS parameter, you will be able to map all the transformations from the 0th frame all the way to the final second frame. Or if you wish, you can also have a frame over here as well. I can label this as X3, Z3. This would be Z0, X0. So another thing is, once you apply the DH parameters, you will soon realize that having the first frame Z1, X1 here, may not be very ideal. It may not be very ideal because after a while, you will not be able to find out a transformation from the first frame to second frame. So in general, sometimes it will be beneficial to move this frame from here to here. So ideally, Z1 would be like this, and X1 would be like this, and Z2 would be like this, X2 would be like this. So obviously the frames are oriented in a different way, but they are more or less coincident. So if you do that, you will be able to get the transformation matrix, but you may not always get it in the first try because it's always a trial and error process. Because as per the procedure, we have first assumed or first assigned the Z-axis as per the direction of the joint. But at the same time, this Z-axis can be positioned anywhere along this axis. It can be at the bottom, it can be here. Does not need to be right at the middle of the joint. And sometimes for convenience, we can shift this Z1 upward and Z2 here so that both of them would be coincident. So yeah, multiple different ways of fixing the frame of reference is possible. And you will get different DS parameters as a result. But at the end, the behavior of the mechanism would still be easily predictable. Okay, so one sample question that we have seen is like we have a triangle with coordinates ABC, which is rotated by about z-axis by 90 degrees in the counterclockwise sense. So if you have a triangle like this, so I'll call this as x-axis and this is y-axis. So point A is like this, 0, 0. Point B is like this, 3, 0. And point C is like this, 3, 4. So this is that triangle. So if you rotate this triangle by 90 degrees, then what would be the new sides of the triangle after it has been rotated? So what do? We simply apply the rotation matrix for each of these points to find out the new points. A dash, B dash, and C dash. From there, you will be able to get the correct answer for after you have done the transformation. So yeah, that's about it. We won't probably solve this, and the correct answer in that case would be option A itself. After you have done the transformation. Okay, that was about week 2. And also there was another sort of question where you are asked to find out the link twist angle. So link twist angle, if you can recall the definition, is nothing but the angle along xi minus 1. So that hold on a second. Yeah, angle between xi minus 1. Sorry, angle along xi minus 1, so that the relative orientation between zi minus 1 and zi are taken care of. So in this case, z2 is like this, going out of plane, z1 is like this. And if you rotate 90 degree along the negative x1 axis, if you're rotating like this, minus 90 degree, x1 would go something like this. So either you can rotate it by minus 90 degree or you can rotate it by plus 270 degrees. Either answers are correct. So in this case, I think the correct answer is option A. You can rotate it by plus 270 degrees also. Both have the same effect. Yeah. Now, what did we discuss on week 3? Now we discussed actually solving some forward and inverse kinematic problems of robotic manipulators. Then we have also seen how to solve inverse kinematics using a numerical inverse kinematic scheme. Because there are not a lot of examples of robotic manipulators where you can derive a closed form numerical inverse kinematics. Now, sometimes you will have to rely on numerical methods. So forward kinematics, we know already what the definition is. And inverse kinematics also, we already know what the definition is. Are there any important points? Yeah, the main difficulty of inverse kinematics is the problems of existence of multiple solutions. So as you can see, even in the case of a 2R robot, like a serial 2R robot, so if this is the ground and if this is the end effector, a simple 2R robot can have 2 solutions. So this is the first solution, what I've depicted here. And this could be the second solution. So even for a simple 2R robot, just with 2 links and 2 joints, it has 2 solutions. So in the case of a serial robot with multiple degrees of freedom, maybe 6 or 7 degrees of freedom, it will have even number of solutions, multiple number of solutions. And it's not very easy to keep a track of all these sort of multiple solutions. And yeah, and sometimes it may not even be possible to solve it, like we solve it for a 2R robot, things like that. So that is where we come across or we rely on numerical methods, which has its own advantages and disadvantages. So the main thing is in numerical methods, we use an iterative scheme. The number of operations that we need is unknown. So we don't know in how much time it will finish. But in closed form, we already know the solution. We only need to substitute the values. We know how many operations are required. And numerical methods will only give you a single solution. Depending on the initial guess or depending on this initial condition you provide, it'll converge to a local minimum. And as a result, you will be only able to get a single solution. But in a in an analytical method, you will be able to, obtain all the possible solutions. And it is much less desirable than closed form solution because it may be a bit slow in real-time applications. And since analytical is much faster, it is applied for real-time control. And in numerical solutions, they can be applied to all sorts of robots. Because this Newton-Raphson scheme can be applied to all sorts of robots. But that's not the case for analytical methods because some robots can have analytical solutions, some may not have. But this numerical method can be applied throughout, and even for a 2-hour robot, you can still apply. Yeah, so that was the difference between numerical solutions and closed form solutions. And we have also seen the implementation of the inverse kinematics using a numerical scheme. Right? It's nothing but using Newton-Raphson, but it's fairly straightforward. But I suppose we don't have to discuss this derivation right now. Yeah, so this was a typical question that we have discussed on week 3, which says out of the given 4 DS parameters, which of them are link parameters? So link parameters defines the properties of joints, Link parameters are nothing but the information between joints. So which basically corresponds to the link twist angle or the link length parameter or the link length. So link twist angle is actually a link parameter. Link length is also a link parameter. So these two are link parameters. And the joint angle and the joint distance are joint parameters. So in this question, these would be the correct answers. Question 3. And question 4, for the following figure, we are supposed to find out the correct, DS parameters. And for your convenience, all the frames of references have already been assigned, Z0, the ground frame is like this. Z1 with respect to this joint, the vertical joint is fixed here, Z1 and X1. Z2 and X2 with respect to this joint, the rotated joint is fixed here like this, Z2 and X2. And Z3 and X3, again, this joint is also fixed like this, Z3 and X3. So with that information, how do you move from Z0 to Z1? How do you move from Z1 to Z2? How do you move from Z2 to Z3? If you use all these 4 parameters, you will be able to obtain the correct set of DS parameters. So yeah, that's about it. I probably don't have to solve this problem now. We have already solved this. Unless if there is a specific doubt, please let me know. We can solve it. Okay, so for week 4, we now moved on to differential kinematics or velocity kinematics. We also have seen the propagation of velocities from the base frame. So I'll draw schematics like this. So if this is the base, and if this is the end effector, so the velocity propagation would be from base to this end effector. the direction of velocity propagation. So if the robot is rigidly connected to the base, or if it is fixed to the ground, the velocities of the base would be zero. And depending on the input that you would be giving onto this individual joints using motors, subsequent velocities would get accumulated. As you move from base to this joint, it will get accumulated. And as you move from this joint to this joint, it will get accumulated. And that is why, that is what this velocity propagation model does. It will take this initial condition and it will propagate from base all the way to the end effector. And we have also seen a phenomenon called singularities in serial robotic manipulators, when that will occur, how to avoid. And we have also given a brief introduction to robot dynamics. Yeah, so moving on, we have this introduction to differential kinematics. This is nothing but the forward kinematics mapping, where mu is the task space variables. And the Q is nothing but the joint space variables. And for velocity kinematics, we differentiate this expression with respect to time, which is nothing but mu dot is given as J of Q multiplied by Q dot, where J of Q is nothing but the Jacobian of this constraint equation. So if you expand it, it will look something like this. Dou function Q vector by Q1 plus dou function Q by Q2 plus so on and so forth. So this function is also a vector function. Then the second line would be dou function, second element of this function by Q1 plus dou function, second element of function multiplied by Q. And yeah, this is about this forward differential kinematics model, where if you have the Jacobian and if you know the velocities of the input joint, the velocities of the task space would be given by this relation. And the inverse differential kinematics would be the inverse of it. If you already know the velocities of the joint as per the motors, then the velocity of the, if you already know the velocity of the end effector, finding the velocity of joint is using this inverse relation. And yeah, that's about it. Okay, so now you may have also come across the cases where the Jacobian matrix is not square. So, for example, if mu dot is J multiplied by Q dot, so if mu dot is 3 by 1, the task space variables, and Q dot is 2 by 1, the joint space variables, and if J is 3 cross 2, so it's like a tall matrix. It has more number of rows than number of columns. So the thing is, we have more number of equations. Yeah, so the meeting may again end within 10 minutes. So please feel free to join back. So in this case, if there are more number of equations than unknowns, so in this case, the unknowns is the joint variables. Q dot would be obtained by J inverse mu dot. But since J is not a square matrix, J inverse does not exist. So then what do we do that? So in case where M is greater than N, or if the Jacobian matrix is a tall matrix, which has more number of independent columns than number of rows, you would find the left pseudo inverse. The procedure is obtained like this, where this is what the left pseudo inverse is. J multiplied by J transpose J, the whole inverse multiplied by J transpose. So you will get an approximate least squared solution. You won't get an exact solution, but it's a least square solution for beside mu dot, what would be your control input or actuator Q dot. That is for this case. An example I can tell you is, if you want to try X, Y, and Z position using a 2R robot with joint variables theta1 dot and theta2 dot, that is where you would use this left pseudo inverse, this one, because you have more degrees of freedom here, but less degrees of freedom here. Right? This is actually a spatial position requirement, but the mechanism, a 2R robot is actually a strictly planar parallel robot. Okay, so another example is when m is less than n. So if mu dot is j multiplied by q dot, if mu dot is 2 cross 1, j dot is, and q dot is 3 cross 1, this will be 2 cross 3. So if you have more variables, but only less number of variables to control. So for example, there are robots like this. It's a 3R robot, which has 3 actuators. But since this is also a planar robot, the only things that you can possibly control with two positions. So in that regard, if you have more number of unknowns than equations, you can actually find out the solution which has the minimal norm. The derivation have already been discussed. So the minimum norm, because in these sort of cases, when there are less equations than unknowns, the system can have infinite solutions. So out of all this infinite solution, we choose the one with the minimum norm. And the procedure to find out the minimum norm solution has been already been discussed. Okay, so I've got a question. I didn't see that. Mu contains geometric variables. Q contain locations of x and y. Am I right? No, yeah, you are right. The second time, it's the opposite actually. Mu basically contains the task space variables. These are the task space variables x and y, and q are the joint variables theta1, theta2, etc. Okay, so yeah, in these sort of systems, when the system is underdetermined, fewer number of equations than unknowns, you may have to treat one of them as free variables, all these sort of things. You will get infinite solution, and out of this, you will select the one with the minimum norm, because it is mostly associated with the solution that requires least energy. Now, this q dot can be associated with the kinetic energy of that joint, something proportional to velocity square. And if a solution has minimum norm, that means that solution can, the energy requirement of that particular solution would be lesser than any other solution. So that is why we would typically go for this minimum norm solution when the system is underdetermined, or when this m is less than n, or in other words, when there are more unknowns than equations. Yeah. So the derivation also we have seen in the lectures. This is for the minimum norm solution. This is the minimum norm solution. So under some constraints, this constraint will have to be ensured. And all these derivations are all straightforward. We have seen in the live session, and we have also seen during the lecture videos. And yeah, during this week itself, we have seen the propagation of angular velocities. So there are angular velocities as well as linear velocities. We have to propagate the velocities from the base all the way to the end effector. So propagation of velocities in the forward direction are governed by this equation. So this is nothing but the angular velocity propagation for rotary joints and for prismatic joints. For prismatic joints, this term does not exist because this is actually the rotary joint corresponding to the current joint. So that does not exist for a prismatic joint. Instead, it has a linearly varying component. So this is angular velocity propagation, and this would be linear velocity propagation for rotary joint and for prismatic joint. And this is that term that I was talking about. This term does not exist for the rotary joint because rotary joint only moves in rotating manner, so it does not have this linear velocity component. Okay. So yeah, we have also seen how we derive these models or how we obtain these models. Yeah, then we have also seen the problem of statics. So the statics is basically nothing but the problem of, for example, if we consider a 2-hour robot like this, connected by two joints. So if you have a problem where, you are exerting some forces, I'll label this as Fy and Fx. So if you are exerting some forces on this end effector, what should be the torque that you need to supply at the joint so that the mechanism remains in static equilibrium? So those sort of problems are addressed by robot statics. The robot is considered to be static. It's not mobile. It's not mobile. And if it is subjected to some forces at the end effector, maybe due to payload or if it is probably holding on to something, then what should be the torques, that constant torque that you need to supply so that the mechanism is in static equilibrium? So those sort of problems are addressed by statics. And here the force propagation and the moment propagation are in the opposite direction, from the end effector frame all the way to the base frame, like so. Because this is where you apply force and you need to successively find out the forces at this joint and at this joint. And due to that matter, the propagation of the forces and the moments will be in the opposite direction. And we do so by, obtaining the free body diagrams or analyzing the free body diagrams of each of these links. So this part is the force equilibrium, and this part is the moment equilibrium for ith link. So you begin from the extreme link, you try to find out the forces and the moments using the force analysis, using the free body diagram, and then you iterate it back to the preceding links. So in that regard, the force and moment propagation, back propagation model would be given by this recursive relations. This is for force and this is for moments. And one another useful thing would be to, just like we do this mapping between task space and joint space for positions and velocities, we can also do this mapping between task space and joint space for forces, right? Forces at the joint space would be the torque that you apply at the rotary joints, and the forces at the end effector would be the forces and torques you. So yeah, we were talking about the mapping between the forces. I'll label this as F in task space, and tau, the torques in joint space. And to get this mapping between the forces in task space and joint space, you apply the principle of conservation of power, which is nothing but the power to move the robot at configuration space is equal to the power to move the robot at task space. So the power is nothing but the force or torque multiplied by velocity. So this is expressed in joint space, and this is in task space. And we also know how this q dot and mu dot are related using this Jacobian equation, right? Mu dot is j of q multiplied by q dot. And if you combine everything together, finally, you will end up with this relation, which is nothing but tau, or the torque in joint space is nothing but this Jacobian J transpose F. That is how you would be able to get this. Yeah, that is about that. And now we also discuss briefly about singularities. So singularities are something, something that you would probably need to avoid, because if the robot actually nears a singular position, the Jacobian matrix could become singular, and the Jacobian matrix could singular. So mu dot is j of q multiplied by q dot, and for some mu dot in this space, q dot is j of q inverse mu dot. So if you consider this to be the input that you have to give into the joint, when this Jacobian matrix becomes singular, this q dot that you would estimate, it may tend to infinity. It may go to a very huge value as when the Jacobian matrix becomes singular, or if its determinant vanishes. And the physical meaning of a singular configuration is that it happens when two prismatic joints become parallel, or when two revolute joints becomes identical, or if it becomes collinear. For example, I'll show one example. If you have a prismatic joint like this, and it moves back and forth like this, and it is connected to a link like this, and yeah, you also have a prismatic joint going vertically up like this. And in between there could be multiple joints, multiple revolute joints like this. So normally these two prismatic joints, this one can control a freedom along this axis, out of plane, and this prismatic joint can control a degree of freedom up and down, along this plane. But due to the effect of the intermediate revolute joints, due to some means, or during some configurations, because of the effect of this intermediate joint, something may happen, because these two joints, may become parallel to each other because of these intermediate joints. So, for example, that may lead to these two joints to be parallel like this. Like this. There are intermediate joints. So if I actuate this joint, I'll get this degrees of freedom. If I actuate this joint, I'll still get the same degrees of freedom. So what does that mean? It has actually lost a degree of freedom. Earlier, it could move like this, it could move like this using these two joints. But now with the same joints, you can only move like this. This vertical up and down position is sort of lost. That is where, when prismatic joints become parallel, you lose a degree of freedom. Or the same thing happens when, two revolute joints become identical. For example, if you have a revolute joint like this, going vertical, and there is also another revolute joint like this, going out of plane like this. And there are some intermediate joints in between like this. So this revolute joint can have two rotations, one about this axis and one about this axis, which is out of plane. And maybe at some configurations, due to this effect of this intermediate joints, these two revolute joints become parallel. So if you rotate this joint or if you rotate this joint, either joint would still give you the same degree of freedom. So again, you would use that degree of freedom because of the singularity. Yeah, but in case of a revolute joint, it does not have to be parallel. It has to be collinear. Then only that motion, that effect would be similar, right? In order for two revolute joint to have the same effect, that two revolute joints should lie along the same vertical axis. So that's what at singular positions, the end effector loses one or more degrees of freedom as the equations become linearly independent. So singular configurations must be avoided as the velocities required to move the end effector becomes theoretically infinite. So you can use this expression to verify that the velocity becomes infinite. So I'll show a small example. So typically an RR manipulator would be something like this, right? So this typical manipulator, this end effector can have two independent velocities, maybe one along this direction and one along this direction. Any two directions, it is feasible. Or I can say one along this direction and one along this direction, two independent directions. But what happens at a singular configuration? So when it is fully stretched like this is actually a singular configuration. So the robot can have a velocity like this along this direction, a perpendicular direction to this fully stretched R. But it cannot have any velocity along this perpendicular direction. Right? So as opposed to two independent directions, at singular configuration, it can only have one velocity along this direction. It cannot have velocity along this direction. And you can actually verify this fact by fully extending your arm. If you fully extend your arm and if you try to push your arm parallel to your full arm, it's very impossible to move like that, right? So that is a singular configuration. So the resistance offered by this direction is infinite, or the velocity to move along this direction is also infinite. So that is what the singular configuration is about. And if you calculate the joint the joint velocities, q dot, at this singular configuration, it may tend to infinity. So that is examples of singularities. And there are different types of singularities, workspace boundary singularities, that one example is this thing, when it is fully extended or when it is fully folded like this, or workspace interior singularities, this occurs when one or more axes line up. And the examples are actually given here, when prismatic joints become parallel and when revolute joints become identical. So that's about singularities. And week 4, we have discussed a few sample problems. If you are given a Jacobian matrix like this, Jacobian matrix is given, the forces on task space is given. You are asked to find out the torque on joint space. And we know from this relation that tau is J transpose F. So you only need to multiply the transpose of this matrix with this to obtain this vector tau. So that is about it. Yeah, now we move on to week 5. We only have half an hour for this session. Is there any specific week that we would like to discuss, or I don't think we can discuss all the weeks by one. Okay, so we'll move on to week 5 and we'll stop when it is actually time. So for the entirety of week 5, we were discussing the derivations of the dynamic model of the robot using two different schemes, using Euler-Lagrange or Newton-Euler method. So this is actually an energy-based scheme, much more easier to derive for smaller robots, but Newton-Euler is actually much more comprehensive, because Euler-Lagrange only gives or only estimates the torques or forces along the actuator axis, but Newton-Euler basically gives you all 6 components of forces and torques, along the actuator components, and all the other directions, which corresponds to the reaction forces. Those forces are also estimated using Newton-Euler formulation. So if your objective is to design the links, you would find the reaction forces to be useful. So if that is the case, then you can use this Newton-Euler scheme. Or if you are not interested in this reaction forces, you are only interested in the actuation torques, you can go ahead with this Euler-Lagrange scheme. So, equations of motion, just like any mechanical system, it can be expressed like so. The torque is nothing but the mass matrix multiplied by an acceleration vector plus a vector which comprises of uh, terms that is contributed by this Coriolis and centrifugal effects. And just like the kinematics, we have actually two different problems in dynamics. The one is called forward dynamics problem, where if you are given an input vector torque onto the motors, what would be the final state of the robot? Final states defined by the trajectory of the robot, by position, velocity, and acceleration. So you can obtain it by inverting that equations of motion like this. And inverse dynamics is, for realizing a particular trajectory, what should be the input torque that you should be supplying onto the motors. So that is about forward and inverse dynamics. And we first covered this Euler-Lagrange scheme, where Euler-Lagrange equations of motion is obtained by this expression, where this term, the scalar L, is called the Lagrangian, which is nothing but the difference between kinetic and potential energy, the difference between total kinetic and total potential energies of the mechanism. And the Newton-Euler scheme is actually defined by two equations. One equation for linear motion, this is the Newton's equation, and the second for this angular motion. That is actually the net torque is nothing but I alpha multiplied by omega cross I alpha, omega cross alpha. And to execute this, you would also need to propagate your accelerations from all the way from base to the end effector. So we have seen this earlier for velocity propagation. Now you also need to propagate accelerations. This is angular acceleration and this is linear acceleration. And the direction of propagation is from base all the way to the end effector. And this is only for rotary joints. And for prismatic joints, you will have a few more terms for this linear components. This is angular velocity, angular acceleration, and linear acceleration. And after that, once you estimate or once you propagate the accelerations, now you back propagate the forces. The first force or the extreme forces would be at the end effector. If your robot is holding a payload, that payload would exert some forces on the center effector, and that effect need to be propagated from the end effector all the way to the base using this back propagation. So that is realized using this, Newton's equation from the free body diagram analysis, where ACI is nothing but the acceleration of the center of gravity, which can again be obtained by this propagation equation. And INI is nothing but the moments, inertial moments. These are inertial forces and these are the inertial moments. And once you propagate all the forces backward, these are the final propagation equations. And these are straightforward obtained by the free body diagram of any links. Like for example, if you have this ith link I, you will have the forces exerted by the extreme end, Fi plus 1. You will have the force at this end as Fi, and you will also have this inertial forces at the center of mass, that is Fi. So that is nothing but this expression. And similar thing can also be said about the moments, because this force will exert a moment, that is basically this term. This inertial force, linear inertial force, will also exert a moment, that is this term. Then you will have this inertial moment from this equation, that is over here. And there should also be, like a force component, there should also be a moment component, Ni plus 1. That is this term. So from a free body diagram, again, you will be able to propagate the moments in the backward directions as well. So this was also a typical question. For a given mass matrix and the Jacobian matrix in joint space, how do you find out the mass matrix expressed in task space? Right? If M of Q is the mass matrix in task space, and M of mu, sorry, this is in joint space. M of mu is mass matrix in task space, and J of Q is the Jacobian matrix. So the well-known or the familiar equations of motion in joint spaces, M of Q, Q double dot plus N of Q, Q dot. Right? We also know this expression from statics. Tau is J transpose F. And from kinematics, we know mu dot is J of Q multiplied by Q dot. And this equations of motion in task spaces, F is M of mu, mu double dot, plus N of mu. Yeah. So if you use all these equations, and if you can somehow bring this equation into this equation using these kinematics and power conservation law, the coefficient of this mu double dot would give you the correct expression for M of mu. Right? We have done this earlier. The three equations that you should be using is these three equations. You may even have to take the derivative of this equation. And instead of this tau, you can substitute it as, I guess, J transpose F. And instead of this Q dot, you can take the derivative and substitute everything in terms of mu double dot. And finally, you will get something in this form. Just take the coefficient of this mu double dot, you will be able to obtain the correct expression for M of mu. So yeah, that is about that question. And you will get the correct answer once you do that. And one more question is from the Euler-Lagrange equation. You have to find out this torque for the single link manipulator. So you know from this Euler-Lagrange equation that torque is nothing but dou L by dou theta dot by dou t multiplied by dou L by dou theta, where this L is Ke minus Pe. So Ke is nothing but half m xc dot square plus yc dot square, where xc and yc is the position of this bob. You can obtain this in terms of L and theta, because yc is L cos theta and xc is minus L sin theta, and P is m multiplied by g multiplied by h. H is nothing but this height. This is nothing but L cos theta. So once you do all these manipulations and once you find out this Lagrangian and once you apply onto this equation, you will be able to find out this torque for this single link manipulator. Okay, so you will be able to obtain the correct solution. And for week 6, you will be able to, we discussed about this.
Sir,
Yeah,
sir,
yes.
week 6 is still not updated, sir, PowerPoint.
Yeah, I was not, I was out of station. I'll try to update everything by today.
Okay,
Would that
sir.
be fine? Yeah, the presentation as well as the lectures, the PPTs,
Okay, sir.
recordings as well. Sorry for that. Yeah, for week 6, we have discussed problems on trajectory planning. We have seen various kinds of trajectory planning. We used straight line interpolation, we used cubic and quintic polynomial, and we have also discussed how a polynomial interpolation is beneficial or its advantages compared to straight line interpolation. We have also seen a case of a cycloidal profile trajectory generation. We have also seen a straight line trajectory with parabolic blends and how that is different from uh, a standard straight line interpolation. So yeah, just to skim forward the topics, trajectory is something but the specification of robot position as a function of time. So you need the position of the robot's joint variable or task space variable as a function of time. That is something what we call as trajectory. And for a straight line interpolation, if you want a variable or a coordinate of a robot to move from an initial position to a final position as per a straight line, you can basically use an equation of a straight line, like so. You know, it's a basic equation of a straight line. But there are a few problems with this straight line interpolation, because if you take a look at this velocity would, well, the velocity profile would look something like this. You know, a rectangular profile. You know, initially there would not be any velocity, but suddenly it will jump to a finite value. Then it will maintain a constant velocity, and suddenly it will drop to 0. And the acceleration would look even more drastic. You know, it will have an infinite jerk at the beginning, 0 acceleration, and infinite jerk at the end because of this finite jump at the finite jump in velocities. So these problems can be solved or can be brought down if you are using a cubic polynomial interpolation, where this is nothing but an equation of a third order polynomial. And with the help of some boundary conditions, you know, if you have initial position, if you have some initial velocity, if you have some final position, and if you have some final velocities, you will have these 4 equations and you have these 4 unknowns in terms of these coefficients a0, a1, a2, and a3. Using these 4 boundary conditions, you will be able to solve these 4 unknown coefficients. And with that, you will be able to, locate anywhere within this point as a function of time only. So yeah, in a typical case, you would probably want the initial and final velocities to be zeros. and initial position to be x0 and final position to be xf. So you'll have four linear equations. You have four unknowns, a0, a1, a2, a3. So if you solve this system of linear equations, you will be able to obtain the coefficients like this, right? And yeah, you will be able to express the trajectory x as a function of time. And in case of a cubic polynomial, if you take a look at the profiles, this is the third order curve, and the velocity would be a second order curve like this, and acceleration would be a first order linear straight line. And there aren't any infinite accelerations at the beginning and end, but there is actually a finite sudden jump to this quantity 6 by tf square at initial and final time. And the sudden jump can be actually brought down if you increase the time, if you increase the time of time for duration, so that the sudden jump will not be, magnitude would be very less. And there is
Sir, I have a doubt, sir, in the
Yeah.
graph.
Yeah.
Now here the acceleration is touching the zero means we will find a point where the velocity change is zero, no, sir?
Velocity change need not be zero. In that point, base simply means that the slope of this velocity is actually zero. That is what this point is actually corresponding to.
Okay, sir.
That does not mean that velocity is zero. Velocity is still not zero. Whatever velocity.
Not velocity, sir. Velocity between the 2 points is the same, where I am thinking. Velocity
Correct.
between the consecutive points is same.
Between consecutive points,
Then only,
yeah,
sir, acceleration is zero.
acceleration is zero, velocity would be same. That is correct. But
Yes,
this
sir.
is
Yes, sir.
this is instantaneous actually. At this point only, that acceleration is zero.
Okay,
So
sir.
at this instant, what it means that there is no acceleration. So if you I don't know what happens if you throw a stone like this as per this path, and if that stone disconnects at this point, it will go on like this because there is no acceleration at acceleration. But since this is instantaneous, in our case, it does not have much physical significance because it's only instantaneous.
Okay, sir.
Okay. Yeah. And yeah, this is only regarding 2 points. Actually, we have an initial point x0 and we have final point xf. But there are also we can also plan this trajectory when we have something called via points. So if I call this x0 and if I call this xf, and this intermediate points, I call this as via points, maybe v1, v2, v3. And maybe in some cases, instead of moving like a straight line, sometimes we may wish to move through all these via points, right? Because if you try to directly move like this, maybe there's an obstacle like this. We may wish to move through all these via points. So there are two ways to plan a trajectory that moves through all these via points. So the first case is when the velocities of all the via points are specified by the user, or yeah, we may again have this meeting terminated in 10 minutes. So I may also require one more session. Please join back so that we can finish this off. Maybe probably 20 more minutes after this. Yeah. So the two cases being the first point when all the via points are specified, and the second case is when the via point velocities are not specified. So when the via point velocities are not specified, what do? We consider that the final velocity of this initial segment would be the initial velocity at this segment. So like we treat this, whatever we have done here, we apply to each of these individual segments. one trajectory planning over this segment, another over this segment, another planning over this segment, another trajectory over this segment. So in the first case, we specify the position and velocity of this via point. And in the second case, we don't specify the velocity of this via point. We simply consider that the velocity of the final velocity of this first segment is nothing but the initial velocity of the second segment, like this. So there are a few implications of that, because if you try to specify the velocity of the via point, there will be a discontinuity in the profiles. I'll see that in this. I'll show you that in the slides. So when the via point velocities are specified, these, you can consider this to be the via point. This to be the via point. And if the velocities of the via points are specified, so this is the first segment, this is the second segment, and these are the individual velocities of the two segments actually. So this is a third order curve, this will be a second order curve, and this is also second order curve. And if you again take the derivative of these segments, you will get accelerations. So this is a linear curve, and this is also a linear curve. So if you consider this point to be the, at the instance of this via point, if the velocities are specified, you can clearly see that there is actually a sudden jump at this point. And this point is the time where we reach this via point. You can see that there is actually a sudden jump between the first segment and the second segment when the via point velocities are specified. So, so in the case where the via point velocities are not specified, you can see that the position profile would look something like this. Velocity would also be a smooth curve, and acceleration, even though there is a small convergence or a sort of a discontinuity like this here, there is no sudden jump like what we have seen over here, and it's more or less connected. It's not discontinuous. So that is why mostly we don't really care about the velocities where we reach the via point, but it is only important that we achieve that position, not the velocities with which we reach that position. Okay, so until now we have seen the third order polynomial. We also have seen the fifth order polynomial trajectory planning, where you can define a joint variable as
Sir,
fifth order polynomial.
quadratic and fifth order, what are the names, whether they are feasible or not?
No, if you can recall, we either use third order polynomial or we use fifth order polynomial. So the order of the polynomial is odd numbered. It's not even.
Okay, sir. Okay, sir.
Yeah, and the reason is that for odd numbered polynomials, you can satisfy the boundary conditions at the end and at the beginning. So if this is the initial point and this is the final point. If you use a third order polynomial, I'll write it here. The third order polynomial can be expressed as theta of t as a0 plus a1t plus a2t square plus a3t cube. So actually there are four unknowns actually, 1, 2, 3, 4. So you require four boundary conditions, which can be that the position and velocity at the initial point and the position and velocity at the final point. If you're using a fifth order, it will be something like this: a0 plus a1t plus a2t square plus a3t cube plus a4 t to the power 4 plus a5 t to the power 5. So how many unknowns are there? There are 6 unknowns: 1, 2, 3, 4, 5, 6. So we need 6 boundary conditions, which are position, velocity, and accelerations at the initial point, position, velocity, and acceleration at the final point. So a fifth order can have control over initial and final accelerations, whereas a third order can only have control up to velocities. It does not have any control over initial and final accelerations. But if you're using odd numbered, the number of unknowns would be, sorry, if you're using even numbered polynomial, the number of unknowns would be odd numbered. So like you have some sort of unsymmetric boundary conditions. You may have 3 boundary conditions here, 1 here, or it may not be symmetric actually if you're using even number of polynomial equations. So that is why we stick with odd number polynomial equations, polynomial degrees actually. So yeah, just like we have seen the third order polynomial, we have this fifth order polynomial, and we have 6 boundary conditions. And if you solve all these 6 boundary conditions simultaneously, you will be able to obtain all these coefficients. If you take this matrix, multiply its inverse with respect to this vector, you will be able to obtain all the coefficients. And yeah, this is the profile for this quintic polynomial, the 5th order polynomial. This position profile is a 5th order curve. This would be the velocity profile would be a 4th order curve. And the acceleration profile is actually a 3rd order curve. And here the acceleration actually starts from 0 and it gradually increases, comes down, and it ends at 0 as well. So it's more or less much more smoother than the 3rd order polynomial trajectory planning. Then we have also seen the case with straight line interpolation with some parabolic blends, where the between these 2 regions it's nothing but a straight line interpolation, and at these 2 extreme ends actually it behaves like a parabola. It's like a curve that follows this kt square. So the time for it to blend into a straight line, we call this as PB, and most often it will be symmetric with respect to initial time and final time. So we call this time as time for blending. And if you take the profile of this planning, since this portion is parabolic or 2nd order, velocity profile would be a straight line or 1st order. And since this is a straight line from TB to this region, the velocity profile would be a constant actually. It'll be constant velocity with 0 slope. And again, since this is quadratic, this portion will be linear. And if you consider this, and if you take the derivative of this plot, you will get the acceleration profile. So this is like a linearly varying linear velocity. So you will get constant acceleration. So this is constant velocity, you will get 0 acceleration. And this is linearly decreasing velocity. So you will get a constant negative acceleration. So your profile would look something like this. Acceleration profile would look something like this. Okay. Then we have also seen trajectory planning, which is similar to a cycloidal motion, where a cycloidal motion is nothing but if you roll a cylinder, a circle or a cylinder over a straight line, the point, and if you trace a point as the circle rolls, it actually depicts a curve, and that curve is what we call a cycloid actually. So if you plan a trajectory as per the motion of this point, the projection of this point onto this time axis. So yeah, that will give you the cycloidal motion. And this equation we have actually derived it during the lecture video, and we have also derived this equation during one of our live session. And here also the joint variable is actually expressed as a function of time. And to get the velocities and acceleration, you are only required to take the derivative of this expression with respect to time, so that you will be able to obtain the velocities and accelerations. So for the cycloidal profile, these are how the position and the velocities and the accelerations look like. And again, here the accelerations are much more smoother. It starts from 0, gradually increases, then decreases, then again further increases. finally ends in 0. Much more smoother than, straight line interpolation or with parabolic lens, or rather, maybe even in the case of a cubic polynomial. And also we have seen a few examples in trajectory planning. You can either plan the trajectory in joint space, or you can either plan in task space. Planning in task space is much more intuitive, because task space is what, as a person, we can easily visualize, because we can visualize everything in Cartesian coordinates, x and y. So if your robotic arm is over here, xi, yi, and if you want to bring it to xf, yf, you can actually plan a trajectory like this, a cubic or cubic, because it's much more easier to visualize. Or you can, at this point, you can use inverse kinematics. You can, convert it into θ1, θ2 initial. And at the final position also, you can use inverse kinematics to convert xf, yf into θ1 f, θ2 f. And then you can plan trajectory from in joint space, from θ1 I to θ1 f, θ2 I to θ2 f. Either ways, it is possible. And there are different benefits for either of these cases. So planning in task space, it's much more natural for the operator to specify, just like what I have said. It's much more easier for us to visualize. It's easier to see, visualize, and check for obstacles. And it's difficult in planning due to planning orientation due to representation issues. That is one drawback that you can say for task-based scheme. And in case of in case of a task-based scheme, you can either use straight path between two positions or circular arc between three given positions. Either ways, you can actually do. So what I mean is that if straight line basically means you can plan a cubic polynomial between xi and xf, right? A cubic trajectory planning between xi and xf, and using the straight line, because if you are moving as a straight line from initial point to the final point, you can use the straight line equation to find out the yi and yf components used. Yeah, if you know xi, you can find yi. If you know xf, you can find xf using that straight line method. Or rather, if you have 3 points, you can also use, find out. You can also plan it as a circular arc, because you need 3 points to define a circular arc. And we have a typical question for week 6 lecture. So in this example, you are given a single link rotary manipulator. So its initial position, theta I, is given as 30 degrees. The final position is given as 70 degrees. And the time taken is given as 20 seconds. And the motion profile is cycloidal. And you are asked to find out the velocity, the maximum velocity, So the procedure is fairly straightforward. You have this equation of the cycloidal profile. You take the derivative of this expression with respect to time. You will be able to obtain x dot of t. But you are also asked to find out the maximum velocity. And the maximum velocity, as you can see, occurs at somewhere around midpoint, actually, tf by 2. So on this expression, if you substitute t as tf by 2, you will be able to obtain the maximum velocity. That is what you can do. So once you do that, you will be able to obtain the answer as 4 degrees per second for these sort of questions. And for weeks 7 and 8,
Sir, so many MATLAB lessons were there. If you share the code, at least we will execute the program, sir.
No,
That
actually, I've talked this to the professor, and he's actually a bit hesitant to share the codes. The reason is that, uh, according to his reasoning, it is that the entire theory has been, discussed. Entire procedure has been discussed in the lectures, and he has also shared the MATLAB codes as he's discussing the lectures. So like
yes, sir. Yes, sir.
sufficient time he actually
Yes, sir.
spends it uh, in each of these discussions where he spends sufficient time with MATLAB. So he says, according to him, he says that if people have to reproduce it, they have sufficient time to reproduce from the lecture video alone, because they can simply pause it and they can type it on their own. But he's
I
worried
am
that
asking, is there any question on the MATLAB code?
questions won't be there on MATLAB code.
Okay,
Because
sir.
he's afraid that if he's sharing the code, then people would simply use it and they won't write
Okay,
their
sir.
own
No
code. So
problem.
that is
No
what,
problem.
yeah, it's mainly for the students
After
actually.
completing the course, then we will try to do that part, sir.
Yeah,
After
yeah,
these 8 weeks, we will do that one. That is
yeah,
not
but
a problem. But
yes,
with the course, we want to at least within the 5 days, at least we can
yeah, with
execute
the
at least a
course, it's
simple program, then we will be happy. Or
yeah,
otherwise, after the course completion, we will try. No problem,
yeah.
sir.
So with the course exams, the MATLAB code is not required, but the real gem of this courses are those simulations. Actually, I think he explains everything with animations also. For a manipulator, how it moves from one point to another.
Or
All sort of
otherwise,
topics.
Other,
Yeah,
otherwise, he has shown the position, velocity, and the acceleration. Karusna sir, can you
yeah,
execute in your MATLAB? Can you show that plot at least? These are only PPT slides where we are you are showing the
yeah. At the
trajectory.
moment I don't have that codes
Okay,
with me, but
okay. Sir.
yeah,
At least we will
but
be happy to see
yeah,
the
yeah. The codes actually, yeah. But I
not
think if anyone wants, they can easily reproduce, because they can, pause the screen and they can, type it on their own, because he spends a lot of time, explaining the code itself actually. So
it is
uh,
not a problem, sir. If it
yeah,
is
but
there in your laptop,
I
within
don't
the
have
minutes we will see that.
I don't
Okay, sir.
have the codes for the
No
I don't
problem,
have the
sir.
codes for that for this
Okay, sir.
course. If I had that, I would have happily,
Okay, sir.
demonstrated that. But I don't have it at the moment. Okay, and for weeks 6 and 7 and 8, we were mostly discussing about motion controls, and the main classification that we were discussing were about kinematic control. And in kinematic control, we discussed open and closed loop schemes. And in dynamic control as well, we have seen similar schemes. Both open as well as closed loop schemes. So we have had this discussion, last Saturday. If anyone wants to see that, I would happily recommend those lectures or those live sessions. But here I would simply like to skim all these topics. So we have discussed the need for a motion controller, because we know that the dynamic models are not perfect, and some of the parameters that we have computed, they may change as time varies, and not all the physics can be modeled in the dynamic model. Maybe, for example, friction, maybe the backlash, all these things, everything cannot be modeled. And there are also factors due to external disturbances. So not everything can be modeled. And as a result, to counter all these unmodeled dynamics, we require some motion controller, which would take this error into consideration and tries to guide the robot along the desired path. So we have also seen evolution of various schemes of motion control, starting from mid 70s all the way to the current era. So earlier they only used exact models. There were no sensing, and later when sensors were there, we used models along with sensors, and then later we used we also acknowledged the fact that sensors may not always be perfect. They may have their own errors. They may have some noises incorporated into them. So how do we take that into consideration? All these things came much recently. Then we have also seen, the steps in control design. The first is to familiarize with the system. Depending on the kind of robot, we may have different equations. So first is to familiarize. Then the next would be to perform the modeling. The dynamic model. We know how to do that as per the recursive Newton-Euler method. Then we have to lay down the control specification, which is nothing but how fast we want our controller to converge. How should be the how much should be the steady state error. How much overshoot there should be. How much overshoot can we tolerate. All these things comes under control specification. And there are control objectives actually, out of which stability of the controller is the most important objective that we wish to ensure. Yeah, then there are the control schemes can be classified as motion-based or model-free control schemes, which fully relies on sensors. We don't use the dynamic model. We only use the feedback from sensors. Or there are model-based control methods, which only uses our dynamic model. It does not rely on sensors. So in fact, model-based is an open loop control, as it is not relying on sensors. Then we have also seen an examples of robust and adaptive control, which are pure definitions as far as our courses are concerned. Then, in the following lectures, we have seen kinematic control, both open and closed loop schemes, dynamic control, both open and closed loops. And we have also discussed this cascaded control last Saturday. It's much more involved than either of these two cases. And it has two loops actually, where an outer loop is a kinematic control. And using that outer loop, we try to control the inner dynamic control. Then there are also a few discussions on further classification, classification on the kind of application that we are using these controllers, the classification on the space concerned, whether we are controlling in joint space, whether we are controlling in task space, whether we are controlling in sensor space. That is also another classification. Then another classification, whether the reference input is constant, not time varying, we call them as set point controllers. If it is time varying, we call them as tracking controllers. We mostly deal with tracking controllers in robotics. And we have actually seen a kinematic control. The first actually is nothing but an open loop control. So we know the Jacobian relation, mu dot is J of Q multiplied by Q dot. So if you want your robot to track a desired trajectory, mu decide, what you do is you simply plug this mu decide onto this, so that Q control input Q dot would be J of Q inverse mu decide dot. So you can treat this as your control input, and this is your decide velocities. And as you can see, since there are no feedback term involved, this is a purely open loop control scheme. And this will only work when mu decide dot is not 0, or if mu decide dot is 0, then Q dot is 0, and this control scheme will fail. And also, we also have to ensure that the initial position of the desired trajectory and the initial position of the actual trajectory has to be equal, at time t equal to 0. Otherwise, your desired trajectory would be something like this. Actual trajectory would be at a different place. But it'll execute probably a similar curve like this, but there is always going to be a finite gap between the desired and actual positions. And robot kinematic control, a closed loop kinematic control, we have also discussed that. Here, our objective is to make the control asymptotically stable, or in a way, as time tend to infinity, we want our actual trajectory to converge to the desired trajectory. So we can do so by forcing this error, which is defined as the difference between desired and actual trajectory. If you force your system to behave as per this first order differential equation, you can guarantee that your system is asymptotically stable. And for that, the control law is as per this. The control input q dot is q decide dot plus lambda multiplied by q tilde. Q tilde is the error term, and in this case, this is actually the feedback term. And how we derive this equation, you can refer our live discussions on week 7. And similar to kinematic control, we also have this dynamic control. So in case of an open loop, we have this dynamics equations of motion as m of q, q double dot plus n of q, q dot. So for a given desired trajectory, q decide dot, and q decide double dot, you simply plug all these things onto this relevant terms, you will be able to obtain the open loop control input. And this open loop control input will only work when this q decide double dot is not 0. Initial positions of the decide and actual are equal. Initial positions of the decide and actual velocities are also equal. Otherwise, just like what we have seen, the actual and the desired trajectory would be always going to be at an offset like this. There is always going to be an offset. So if this is the desired trajectory and if this is the actual, if this condition is not satisfied, there is always going to be an offset, like so. And similarly, for the closed loop condition, we actually want our our error to behave as per this error dynamics, second order error dynamics. Just like in case of a kinematics, we wanted it to follow a first order error dynamics. So if this is how we want our system to behave, if we force our system to behave as per this differential equation, our the q decide and q decide dot will asymptotically tend to 0 as time tend to infinity. So if that is the case, then the control input would be as per this equation, where these two are the feedback terms. So that makes it a closed loop controller. So actually, we have seen a question regarding week 7. This is for week 7, taken from week 7, question 3. So if QD and Q decide are the decide joint positions and velocities, then the computed velocity control can be given as. So the computed velocity control is as per, we have seen it earlier. Q dot is Q decide dot plus lambda multiplied by lambda Q tilde, right? Q tilde is nothing but Q decide minus Q, difference between actual and the decide positions. So with that, I think the correct answer would be this. And the question also asks you to identify the feed forward term. So in this case, this is the feed forward term, and this would be the feedback term. Yeah, that is indeed the correct answer. And from week 8, we have also seen that the desired trajectories are given in task space actually. So so the control law as per the trajectory in task space would be given as this. But in reality, we would be supplying the control input to the joints. So even though the trajectory is defined on task space, the control should be defined on joint space. So tau would be m of q double dot plus n of q dot. So if this is the controlled law in task space, how do you write the control law in joint space? So you are given a hint, actually. You are given m of mu in terms of m of q, mass matrix in task space in terms of mass matrix in joint space. So if you substitute this over here, and if you substitute this over here, and you know from principle of conservation power that tau is J transpose F. So instead of this F, you substitute this over here, right? So F becomes J inverse transpose tau. So if you substitute this here, and this equation here, and this equation here, you will be able to obtain the control law tau in task space, sorry, in joint space. So with that, I think the answer would be, I think this should be the answer, I think. We have discussed the same problem the previous Saturday. So if there is any doubt, please free to visit that. I haven't uploaded the recordings yet, so mostly I'll upload the recordings for the previous week as well as today's lecture by tonight itself. Yes. Okay, so with that, I'm winding up the session, this session for mechanics and. Okay, so when can you access? You can access all the recordings until week 7. Right now, it's available. It should be shared with you. I think from that website, it should be shared. So the previous Saturdays recordings as well as today's recordings, I will try to upload it by tonight itself. At the max, it will only go by tomorrow. So yeah, by tonight or by tomorrow morning, it should be available.
Sir, what will be the next continuation subject on the robotics, sir? What will be the best one? Where you use, this is the basic one, sir.
No, there is also one more course offered by Professor Shantakumar that is about wheeled mobile robots. That is more about robot motion. Mobile robots with wheels as a means of locomotion.
This
That
basic is enough for next semester.
Yeah, next semester that will be available. But there is also much more involved course offered by IIC Bangalore. And I think there are also several other robotics courses offered by other faculties in other IITs.
Yes,
But
sir, but I am asking continuation of this one, because we are
Continuation of-
slowly developing. We are slowly developing.
a continuation of this, it depends on your interest actually. Like if you are more interested in the mechanical side, there is actually a more advanced course offered by Professor Ashitava Ghoshal of IIC Bangalore. So that again mostly deals with the mechanic side of serial as well as parallel robots. If you are interested in control, if you are interested in motion control of robotic manipulators, then you may have to go to that side. The linear control or synthesis of control courses. Or
I
what
told you,
else?
sir, Kuka robot. What will be the best course to understand the pixel?
For Kuka robot, this course itself is perfect actually, because whatever you need to do, maybe if you want to derive the kinematics, you can use the DS parameters. You can apply the DS parameters on this Kuka robot.
Okay.
You can obtain the kinematics for that. If you have any doubts, you can actually mail the faculties directly. They are happy to guide you. If you have any mails, if you have any doubts on modeling this Kuka robot, you can mail Dr. Shantakumar. You can
Okay, sir.
you can refer that you have participated on this course.
Yes, sir.
And as a team member of his group, we will also be able to help you. If you want any sort of support.
Actually, still I have not started, sir. Now I have done the going to complete this one. Then I will touch the that robot and what is the software, etc. So I'm
Okay. So
going
the
to
easiest
use.
thing is first do this DS parameters, apply this DS parameters, then do this forward kinematics.
Okay, sir.
KUKA robots will have, depending on the KUKA robot, it will have probably 6 joints. If you move one joint, what will be the tip of the joint?
Okay, sir.
If you move one joint, so if you move the first joint, how will that tip move?
Okay,
If you
sir.
move the second joint alone, how will that tip move? If you move the third joint, how will that tip move? All these things you can do with forward kinematics. That is actually very easy. You only need to study
Okay,
the
sir.
DS parameters. Yeah, the DS parameters. That's all. But I couldn't do that simulation on time because I was not in the campus actually. So yeah, sorry for that.
Sir, we were encouraged with the help of your live sessions,
Yeah.
and we got confidence. And
Yeah.
you are very regular, and we are also very regular to listen your
Yeah,
class. And
I am actually
I
thankful that you are
I am
also.
very thankful to you. Even one person or two persons are existing, still you are continuing the live session, sir.
I
But
have to
I
continue actually.
recommend that even for live session, if you give some 1 mark at least per week, 1 mark, maybe the students may be interested in joining the live sessions.
Yeah, but
This thought
maybe
now I got, sir.
yes. So probably the live sessions may not be needed for others. Probably I don't know. But I thought maybe we
Maybe,
can.
sir. Okay.
Yeah, I mean it's fine. It's fine either ways. But anyway, like even with 0 participants, I have to do this live session actually. So that is another thing. But it's still fine. No problems. No worries.
Thank you very much, sir.
Thank you. Thank you very much. So with this, I'm winding this video unless there are any more questions. Okay, so I've got a question. Is it sent to our mail or you can? I think you can access from the website. Yes, you can actually access it from the website. The recordings as well as the PPTs, you can access it from the website. Yes. Okay. So yeah, with that, I am winding up this session. Thank you. Thank you. Thanks for joining. Thank you.
Sir, may I know your mail ID, sir? Is it possible?
My email ID, is it not available through the website? It's
I have not seen, sir. Which website?
it
NPTEL
should
website.
be NPTEL. Yeah, as a TA, I think it should be available, I think.
Okay,
But
sir. I will
it's
search.
very difficult. I'll type it in the message 132
Okay,
double
sir.
one four double zero one at the right address. Yeah, I hope you can see that. That is my email
Okay,
ID.
sir. Okay. Thank you, sir.
Is it enough to go through the assignments for the final exam? Yeah, I think it's more than enough. You can expect similar sort of questions for final exams. Questions discussed during these live sessions as well as questions that you have practiced during the weekly quizzes. You can expect similar questions for your final exam, more or less. Okay, so yeah. Week 8, question 7 discussed today is from where? Week 8, question 7. This is from the previous live session, live tutorial session on week 8. So I haven't uploaded this on, I haven't shared this yet because I was not available. I was traveling actually. So I'll make sure that this will be uploaded today evening, today evening itself. So hopefully it should be available by tonight. The entire recording should be entire recording of this discussion should be available by tonight. Okay. No, this was a sample. This was just a sample. This is we are not discussing any questions from the assignments. These are all sample questions. We are not discussing assignment questions, but they are very similar, very similar actually. Okay, thank you. Okay, so that's it. Thank you.